Let's continue with alumina-based ceramics. Ceramics are mostly composed of high purity aluminum oxide, and that's why in this textbook it's sometimes called as aluminum oxide or ceramics. They are almost equal to each other, and in the industry sometimes they call it as white ceramics. The tool material actually we are using in the production of these specific cutting tool for various machining operations. So why do we prefer to use ceramics? Since they have high abrasion resistance and high hot hardness values. And another importance is that they are quite chemically stable, and you can easily use them at high speeds. They have less tendency to adhere to the metals during the machining operation, and obviously we have less tendency for an build-up edge. And due to these reasons, we prefer to use them at high speeds on the machining of metals. Another advantage is that we can obtain good surface qualities. Surface roughness values are very low since we don't have any chemical, let's say, reaction between the cutting tool and the workpiece material. Due to that, we have pure surfaces having very low surface roughness values. But the problem is that the toughness value of the ceramics are not good, so we cannot use them in interrupt cutting operations. Instead, we prefer to use them in high speed and uninterrupted machining operations. We can call them as actually finishing or semi-finishing operations. We have a nice figure here showing the relation between strength and toughness and materials, and on the y-axis we have hot hardness and wear resistance. So we know that hot hardness and wear resistance are related to each other. On the x-axis we know that toughness is somehow related with the impact strength. Now let's have a look at these one by one. High-speed steel, as you know, has the highest toughness property, but it has one of the lowest hot hardness property. After some temperature, the hardness values of these cutting tool materials decreases. Then let's have a look at something here. As you see, it has the hot hardness, maximum hot hardness value, the CVD diamond or single crystal diamond. But their problem is that their toughness, impact strength is very low, which means that you cannot use them in interrupted cutting operations. They are mostly preferred for continuous machining operations like finishing, semi-finishing operations. On the other hand, we have a group here which can say that they are kind of suitable for most of the applications. Their strength and toughness properties are acceptable, and they also hot hardness and wear resistance are also fine. But the ideal material is somewhere here, and these days we don't have such a material whose strength and toughness is good, and also its hot hardness and wear resistance should be very high. But right now we don't have such a material. Maybe in upcoming years, 10 years, 20 years, we may have such a specific material having all these perfect mechanical properties. Then we have ceramics. Ceramics are actually a combination of ceramics and metals. Cer comes from ceramic and met comes from metals. That's why they call it as ceramics. And in this type of material, we have a metallic matrix, and inside this matrix, we have ceramic particles. And since we have metals inside, it's not purely white, and that's why sometimes people call it as black ceramics. And about 7% of aluminum oxide is again inside this matrix. We may have 30%, the rest is composed of titanium carbide, and furthermore, depending on your again specific requirements, you may have different types of carbides. And we know that they are chemically stable since we have ceramics inside, aluminum oxide inside, but the thing is that they are quite brittle, and you need to be careful about build-up edge formation. They might be quite a problem depending on the type of workpiece material you are using. Then we have a bit harder material, cubic boron nitride. This is an artificial material, is abbreviated as CBN. and it was developed around 1962, and its trademark name is Brazen. And in this one, we have actually polycrystalline cubic boron nitrides, and the layers of these materials are not too much, not too low. About 1 millimeter is quite thicker compared to the other types of coatings, and we do manufacture them with the help of again powders under high temperature. So we put them onto a kind of a mold and then apply some pressure at high temperatures, and then these particles are joined together, and now we can use them as a cutting tool material. And in addition to their nice hot hardness values, they also have high wear resistance, and their cutting edge strength is quite good. You see how we can use CBN. We need to have a kind of a base, tungsten carbide insert. This is the conventional carbides we discussed in a moment ago. And then we have a little connection brazing. And then we put carbide substrate, and on top of it, we put this CBN, polycrystalline CBN, or a little diamond layer. Once you have it, then you can use it for the machining of difficult materials. Then we have specialized ceramics. This is called silicon nitride based ceramics. It has good toughness, hardness, and thermal shock resistance properties. Its trademark name is Sialin, since it's composed of silicon, aluminum, oxygen, and nitrogen. And it's mostly preferred for machining cast iron, nickel-based, some superalloys. And the thing is that you shouldn't be using them at very high cutting speeds, as in the case of diamond. You should keep it at intermediate values. And due to the chemical affinity actually with the iron, like in the case of diamond at a special elevated temperature, it's not preferred to use, not suggested to use that for the machining of steels. Then we have the hardest material, actually natural hardest material. This is diamond, and we know that it's actually useful for high wear resistance, high hardness values. But again, another thing, it can easily maintain its cutting edges, like in the case of actually silicon nitride and cubic boron nitride. Their maintaining sharp cutting edge ability is better, much better compared to the other primitive cutting tool materials. And with the diamond, as we discussed a moment ago, we can have good surface finish, and we prefer to mostly use them for finishing or semi-finishing operations. And as I mentioned while we were discussing diamond coatings, we cannot use them for ferrous metals, but we can use them for non-ferrous alloys and other metallic materials. Then this is the last type of cutting tool material, a very special one, and this is called viscous reinforced materials and nanomaterials. It's not a specific type of material, but it's a kind of a metallurgy. What we do in this approach, we actually embed short fibers into these materials so that their mechanical properties will be improved, like fracture toughness, resistance to thermal shock, cutting edge strength, creep resistance, and hot hardness is improved with the help of these short fibers inside the materials. And these are called as also named as composite materials. And the fibers are not too long, as you see. Their length is about 100 micrometer and their diameter is about 1 micrometer. But obviously they are quite costly, so you should be deciding on these depending on your extra requirements. Let me talk about what to do when you're actually cutting tools, cutting edges becomes dull. You can first of all do some resharpening. If it's possible, you can make use of some special grinders, grinding machines, so that after these resharpening, you will again have sharp cutting edges and perform the machining operation once again. But if it's not possible, then you may simply do recycling. There are some specific companies where they collect such cutting tools and do recycle them and try to decrease their overall cost. And you can have a look at here typical costs of different cutting tool materials. For instance, if it's an uncoated carbide, it's around $10. But if you do coat them, then the cost is increased. For ceramics, we have $50. But on the other hand, if you are using some diamond coated or cubic boron nitride and diamond, then the cost is usually more than $100. Let's have a look at cutting fluids. So first of all, why do we need cutting fluids? Since we have some problems in machining, for instance, we have high temperatures, we have chips around, we are applying too much energy. And with the help of these cutting fluids, we are trying to eliminate or at least decrease the effect of these problems. What are they? For instance, we have friction problem. Once you use proper oil, let's say, then you can decrease the friction or the coefficient of friction, and with the help of it, you can increase the life of your tool. Since less heat will be transferred to your cutting tool, its temperature will not be increased too much, and its shape will be almost the same, and you can use it for maybe, let's say, some months. Another function of cutting fluids is that with the help of special coolants inside these cutting fluids, they can carry away the heat generated and decrease the temperature of this cutting zone. And once the temperature is reduced and you have less friction, then that means with less forces, less energies, you can do the machining operation. Another function of the cutting fluids is that they simply carry away the chips generated in the environment so that we will have less scratches or less chips around. And lastly, since they are again, especially oils, have a kind of a protective barrier between the cutting tool and the workpiece, the corrosion problem of workpieces actually eliminated. And for the cutting fluids, actually, we mostly use water and oil. Water is a perfect coolant, actually. It carries away the heat, it decreases temperatures, but it does not have any effect on the lubrication. It cannot decrease the coefficient of friction. And that's why for that purpose, we prefer to use some types of lubricants. What are they? The most popular one is simply oil. So if you kind of have an emulsion of water and oil together, then that means your cutting fluid will act as a coolant and also act as an lubricant. This is actually the most common approach in machining operations. Here you see the types of cutting fluids. We have 4 of them, and we will be covering also section 33.7. There's nice discussion about the types of cutting fluids, but let me quickly go over these here. Oils, as I mentioned, they're nice lubricants. They're not perfect coolants, but once they are used with water, they actually perform well. Then we have emulsions. Emulsions are a kind of mixtures of oil and water together. And furthermore, you may also add some specific additives. And with the help of this special mixture, we can reduce the temperatures and also reduce the coefficient of friction. Then we may have semi-synthetic type of cutting fluids. In these ones, we have little mineral oil and water, but no other oils or other kind of things. And in the synthetic ones, we don't have any oil, but we mostly have some chemicals with additives, and also they need to be diluted in some amount of water so that the amount we have will be increased. So how do we apply actually these cutting fluids into the machining operation? We have some methods. As you see, fluiding is one of the easiest and the popular one. I'll show you an example here. These are some machining operations. The first one is turning operation, milling, thread grinding, and drilling operations. So we have some poor and good actually fluiding operations. In the fluiding, we are supplying this cutting fluid into the cutting zone. And if you, for instance, in this drilling operation, apply your cutting fluid on the workpiece, then it will not be as effective as if you apply right into the cutting zone. So this is the best case for the drilling operation. And on the other hand, for turning, this is an poor application. You need to again apply this cutting fluid directly into the cutting zone. Then we have the mist type of cutting fluid application. It's very similar to using actually aerosol cans. So with sprays, you can apply this ladle fluid into the cutting zone. And this is sometimes preferred in specific applications. Then we have high pressure systems. And in this case, the main aim is actually increase the rate of heat removal. So somehow similar to fluiding, but in the fluiding, we don't have high pressures. In the high pressure systems, as the name implies, we have powerful jets and they are applying this cutting fluid right into the cutting zone. Then we have through the cutting tool system. This is one of the most effective type of actually cutting tool application. Here we have an example here. As you see, the cutting fluid is actually moving through the cutting tool. This is another image. Actually, this is showing a temperature distribution. In this one, we are applying the coolant onto the chip, but in the below one, we are applying the coolant through the tool. So that's why actually we have a uniform temperature distribution, but if you look at the other one, we have high temperatures here. And this is quite difficult to apply, but once you have such a system, it is much more effective than the previous types of cutting tool applications. And how do we decide on this cutting fluid? We need to check the type of workpiece material we are machining, the other components, the tool components on our machine. We need to consider the biological things, whether some bacteria will actually grow or not. We also need to consider the environment, since some of these cutting fluids are not recyclable. We may harm environment, so we should be aware of these and try to select our cutting tool material accordingly. And this is actually the last topic of this chapter, near dry and dry machining. Why do we need to apply or use such approaches? Since considering again economical and environmental reasons, we need to decrease the amount of work fluids, cutting fluids using. Once you decrease the amount of cutting fluids, then we will do less harm on the environment and decrease the cost of our machining operations. In the near dry cutting, actually, as the name implies, it's not completely dry. We apply little amount of air fluid mixture so that at least some the temperature of the cutting tool will be decreased a little bit. We have some special applications like through the spindle, but it's quite difficult and expensive. And the dry machining, obviously, as the name implies, we don't have any cutting fluid. We prefer to do it without any such special oil, water, or other type of cutting fluids. And the last type of such machining is called as cryogenic machining. Again, as the name implies, we need to use cryogenic gases like nitrogen, carbon dioxide. With the help of them, we will be reducing the temperature of these cutting tools tremendously and in a shorter time, since we will be using them in liquid form. And as you see here, in liquid form, the nitrogen has a temperature of about -200 degrees Celsius, which is very low. So with the help of it, we can even use high-speed steels for the machining of difficult materials. And that is all for chapter 22, and I will be discussing chapter 33.7.